the heavy homework, i.e. homework plus midterm, assigned by 6/24, 12 p.m. or 12 noon. A study guide and review for the material. I don't exactly know about a study guide. I can certainly cover general topics. I try not to have any surprises. I'm not trying to ask questions that trick you or anything like this. It's more, to the best of my ability, I'm trying to convey certain ideas. When I emphasize things, it's because I think that they're important, and those might have a higher likelihood of showing up on the final exam. Roughly speaking, those would include, I'll try to put something else together like this closer to next week, but probability spaces. Can you create them? How many questions on the final? Depends. 5 to 10. If there's 10, there will be some lighter questions. True, false, multiple answer, this kind of thing. If there's 5, then there won't be any multiple choices, but yeah. The final exam, hold on, one thought at a time. So, probability spaces. Independence between events, random variables, also aka probability distributions. That will include expectation. That will include variance. And linear regression that can be done on paper. So linear regression, this Thursday, I will be showing you some stuff in Excel. I'll be talking high level, drawing pictures and stuff on my computer about how linear regression works. This Thursday, I will break out Excel, but there's going to be no Excel questions on the exam. That's just purely, you walk away from this exam, or from this course, you have some exposure to being able to take these ideas and put them in some program to give you answers or that match the theory that we talk about. So expect questions on linear regression during the final, but it will be nothing that you need to use a computer for. At the most, it will be just stuff you can work out on paper. You shouldn't need a calculator, anything like that. But yeah, so therefore there'll be more fundamental kinds of questions. They might require some computation as far as doing some algebra or something by hand, and that's the majority of it. So these are the highlights. We're talking about probability spaces from the very beginning because we need to build up to statistics. Statistics is random variables, expectation, variance. These things are useful to know because you can make a line fit through points. And making a line fit through points means that you can take data and make predictions given that data. That's it, in a simple way. Simple though it may be, very useful, widespread usage. So that's it. Yeah. Now, what else? What was the other question? Leaving a study guide, yeah. So study guide, I'll do that as soon as I can. Maybe late this week, maybe at the latest, very, very early next week. But I've basically written out the highlights in our chat. I have a question regarding the first question of our homework. So I want to address that. Let's see. Yes, about disjoint events. Great. For the student who asked this, would you want to unmute yourself to delve into it a little bit more?
Are you referring to me?
Let me look. Yes, great, yes.
Yes. I have like a inkling of a feeling that I did it wrong, and that was the one I felt most unsure about when I was doing homework. I just wanted to see it again if I had the right logic on it. Let me look at my notes real quick.
Right. So this is about an event E and a different event E prime.
Yeah, exactly.
Where in the first case, you have that the probability of E and E prime happening is equal to the probability of E plus the probability of E prime. In a second scenario, you have the same thing, the probability of E and E prime, as being the probability of E plus the probability of E prime minus the. I'm sorry, these are unions. The probability of either of these events occurring as the probability of E prime intersect E intersect E prime. Okay. So this question is about why are these two things different? They're both correct, but they're different depending on the scenario. And in some scenarios, you should use number one. In other scenarios, you should use number two. In particular, you use number one on disjoint events. And on number two, these are non-disjoint events. So my question was, in the case that you have non-disjoint events, how do you come to number two? What is that about? In particular, why is there this extra piece that you take away? Other than this, they're the same. But there's this piece that you subtract. So showing that this is true, and a bonus for if you can give an explicit example. That means like some real world example or whatever where this applies. So now that I've described the problem, what is your question about it?
I would just like to see the question working. That's really I'm not sure if the example I gave was correct. I gave two. My example was rolling a die and then flipping a coin, but the math seemed off to me when I calculated the probability with the but I'm not sure.
All right. Pick a different color. rolling a die, then flipping a coin, right?
Yep.
Right. And you think that this is an example of which? Number 1 or number 2?
I think it's a disjointed event.
This is a disjoint event. Okay. Why is it a disjoint event? You're corrected.
Because they have no they're not conditional on each other. That they're not connected. They're two separate events. Yeah, if that makes any sense.
It does. Yes. Yes, that makes sense. So, pictorially, what disjoint events are, if this is your probability space, disjoint events look like this.
I can't see anything on the screen.
Oh, no? No?
No.
Just a moment. Why? Okay, let me stop sharing it and share it again. Have you not been able to see anything this entire time?
No.
Ah, okay. Well, that's not great. The screen says it was being shared, but... Alright, can you see it now?
Yes.
Okay, great. Boy. Alright, so...
I think the equation I used was the second one.
Okay.
Where you subtract the probability of both events happening from adding the two previous.
That you should do in certain circumstances.
Okay.
In the case that you roll a die and then flip a coin, and these are two events where one does not influence the other, then you have this scenario where the E and the E prime here, this is a joint probability space that considers all of the possibilities of rolling a die and then the probabilities of flipping a coin. Both of those things taken together. So, for example, where's my pen here? See what the same colors. This might be, for example, 6 heads and 3 heads and 1 heads. So, rolling odd and flip heads. Where this event, E prime, might be, let's say, this thing. Nope. 3 tails. 1 tails. So this is rolling odd flip tails. Okay, so this is a joint probability space. Each of these events, you described one event of rolling a die and flipping a coin, which means for each event there's 2 components of it. There's what you get for the die roll, and then there's what you get for the coin flip. Now here, these are disjoint because on a single roll of a die and a single flip of a coin, you're not going to get both heads and tails. You're going to get one or the other. So this is one example where these events are disjoint. They share no commonalities.
Okay.
Let me move down to an example of number 2. This is a picture that looks like this. Epsilon prime. So, in particular, there's this middle area of overlap. And this is epsilon intersect epsilon prime.
Mhm.
So when you consider the probability of this one in the blue, you can calculate whatever area the E circle takes up plus the area of the E prime circle. And so one happening or the other is just the sum of the two. In the second case, you can take the sum of E and you can take the sum of E prime, but you're double counting. You're double counting because there's this overlap.
Yeah.
And so you need to take that away. So an example of this might be, e.g., I don't know, one color. E.g., roll odd flip heads versus roll one flip heads.
Okay.
Something like that. So there's an overlap between the two. Where in the second case, these things depend on each other. Like rolling a one and flipping heads is a part of the outcome. Excuse me, the possible outcomes of rolling some odd number, any odd number, and flipping heads. So these lie on top of each other, whereas up here they don't. And so this is the difference between 1 and 2. My question was regarding number 2, and something like this would be fine. You draw some pictures, these things overlap. You need to take away the overlap to do stuff, and the extra credit would be something like this, some concrete example of when that happens.
Okay.
Yeah.
All right. Thank you.
Yeah. All right. There was, be it this question or the other two, are there any questions about this? I can give 5 minutes for either question 2 or question 3. If there's no questions about them, I will just move on into today's lecture. Let me give you a chance to speak up. Okay, well, then let's continue. So we've done homework review. Let me go ahead and touch base really quick on linear regression because we threw this in at the very last minute from last lecture. So the abstract idea is that you have points, here being circles in black. Here there's 4 points. There's a point at 1, 1. There's a point at 2, 2. There's a point at 3, 2. And there's a point at 4, 4. And I've drawn a number of different lines. One, which somehow people just kind of agree, it's a bad line. It doesn't work. But when you get to the green versus the blue line, it's harder to tell which line is better. The last class, we had a student suggest that the green line is better because it actually passes through 3 out of the 4 points, which is a valid way of thinking. That could be the case, that the green line is better. It could also be the case that the blue line is better. And the blue line could be better because even though it doesn't pass through any of the points, the distance from the blue line to all of the points added up, so these little red lines here, is that of a length less than 1. So here I'm calling the error in the green line the summed distance between the line and any of the points. Because it passes through 3 out of the 4, in 3 out of the 4 cases that error is 0, which is good. But in this third point, it has an error of 1, which is bad. The question is this error of 1 greater than or less than the blue line? And whatever the distance this is between point 4, whatever this distance is between point 3, whatever this distance is between point 2, and whatever this distance is between point 1. If these red lines are smaller than 1, because that's the distance between this green line and its penalty, its error, then the blue line is better. And that is the high-level explanation of what makes a best fit line. You can draw an infinite number of lines. I mean, here, the orange, that's a bad line. I could come up with an infinite number of bad lines. I can come up with an infinite number of lines between the green line and the blue line. But out of all of this infinite number of lines, there is one, exactly one, that will be the best line. And the best line is the one that has the smallest score, where the score is the sum of the distance between the line and the points. That's the error. The line didn't pass through the point. The line is far away from the point. How far? Well, at that point, how far is the closest distance from that point to the line? That's the error. You square this for reasons that I'll get into. And for every single point, you calculate the error. You add all of the errors up. And for any line, given that you have all, like the total error that these lines make, you want to choose the one with the minimum error. And that's it. Basically, I mean, this sort of just encompasses everything that we're building up to. There's different ways that you can think about it that are useful. In particular, the fact that this is a variance. This is important. And we've talked the last class more about expectation, or otherwise the average. The average expectation. Right now, you can think of these as the same things. The variance is how far on average things are different than what you expect. Not everything is the same from what you expect. Actually, I think I drew something here. Let me go to this. By the way, these notes should be available on Blackboard now. Right. So here is an example of two different lines. The same line, actually. Same line. So you expect the same thing. But the line on the left has a higher variance. That means that the line is further away from most of these points, or actually that each of these points lie further away from the line. That's a better way of thinking about it. Than these points. These points, not all of them lie on the line, but they're closer to the line on average. So it's from that perspective that you score lines. You don't have to draw an infinite number of lines. You can just calculate a score and choose the minimum. Whichever line has the minimum variance, and that is the best line. So, in any case, these are two different lines, although they have different variances. For each of them, to find the best line, you make whatever this variance is as low as possible. If I draw, I mean, here, that's a bad line. This is higher variance. Why? Right. This line is higher variance, right? I mean, like, look at how far away it is from all of these points, right? It's just sort of like far away from everything. This is not a good line. Bad line. Because it's far away from all of the points. In this example, this would be a good line, because although it's far away from points compared to the right, it's as close as it can be as possible. All right, so that's the high-level picture of, given some set of points, how do you choose among all of the different lines, all of the literally infinite number of lines that you could draw? How do you choose the one, the single best one? You choose it because every single line you can give a score. Its score is, in some sense, the distance of the line to all of the points. And you add all of these up. Here, for example, this point, boy, different colors. This point here, the orange line is better than the blue line. Why? The blue line here is further away from that point. So the orange line for that point is better. But if you look at all of the points, the orange line is no good. The orange line is worse than the blue line. All right? So that is you pull back and sort of the big picture idea. We will get more into this on Thursday, but today I wanted to introduce this sort of big picture concept of, as I said in this course, what I want people to build up to is, given a cloud of points, draw a line through it. And not just any line, the best line. And the best here, I'm defining in this way, that the line is closer to all of the points than any other line could be. All right, let me pause for a moment, and I want to open up the floor because that's the big picture. And if you don't understand it, I want to spend some more time on it. Because, like the math, these just, I don't know, it's a way to calculate stuff. But more important than that is understanding the big picture. Like, what are you doing? What is this math supposed to be leading to? So,
If,
um,
if I'm if
yes.
I'm reading this correctly,
Mhm.
you take the difference in x between the lines and square it, basically.
Yes.
Okay. Okay. Yeah.
Right. So when I'm saying the distance from the line, technically it's the squared distance. And there's two reasons for that. But for the sake of the picture, just imagining the line being far away from the points. The
Mhm.
squaring, because it doesn't matter. Is the point above the line or below the line? The point is far away from the line. So that's one of the reasons for having a squared value. Um, by squaring things, there's no negatives. You can't have one point above the line canceling out a point below the line. They both are bad, and so if you square it, the line is penalized for both.
Gotcha.
All right. Thank you very much for the question. That's good. Having questions are good. Double checking stuff, doing sanity checks, um, stating in your own words the things that you understand me saying. All of these are very important. Yeah, they're important checks of your own understanding. Okay, I'm going to pick one person at random and have them reiterate to me what the big picture is of this. How about Royston? You have a mic? Okay, let me check on Rumel. You seem new. That's not good. I see that there's a hand raised thing. So, yeah, Rumel? Muse? Okay, also not here. How about eating?
Hi.
Hey. Right. So, just in your own words,
Mm,
explain to me the big picture behind what linear regression is, or how you find a best fit line through points. Like, what's just the big picture idea of it? You don't need to use any math or anything, just like, how do you understand this now?
I think it's a line of with most points.
A line with the most points?
Yeah, always the average points is like uh mini points and the cell average points.
What does it mean to be an average point? Or you might very well have like the right idea in your head. I just want to make sure that I understand what you're trying to convey. So you mentioned average points. What
Yeah,
do you mean by average points?
like there are 2 points and the average point is in the middle, like this.
Okay, so if you were to, between 2 points, have a good line, ideally for 2 points, it would pass in the middle of these. And it would be the average of them both.
Yeah.
Okay, great. Excellent. Perfect. Thank you.
Thank you.
Thank you. All right, let me repeat myself. Eating is exactly right. The intuition that if you have 2 points, the best point would be the one that's exactly in the middle of these two. But in linear regression, you're not just dealing with 2 points, you're dealing with many, many, many points. So you should choose the line that is the closest to the collection of points. It might be, for a particular point, you might be sacrificing yourself by making yourself far away from it, but you make up for it because you're closer to all of the other points. Okay? As an extreme example, extremes are an excellent thing to think about. Any examples about anything, blow it up into something big, or make it something really simple. Let's take these points. These points are basically all on a line. So that's a good line. It basically goes through all the points. Sorry, I'm not drawing exactly. Imagine it goes through all the points. Now, imagine that I add a point here. Now, this line becomes really bad for that point. That's a big error. It's a small error for all of the other points, but here, that's a big error. So maybe having a line that's like this is better, because yeah, it's bad for each of these, but it's closer to that point. So here is, I'll just use one big B, big error. And then all of these are small errors. So this is like an extreme example, but hopefully it illustrates the point. You don't have to pass, the goal isn't to hit as many points as you can. The goal is to, whatever these lines are, the distance from the line to the points, add them all up and create a big line that's the error, like here. So here, this is an error of 1, and then we have a bunch of little errors here for this example. Here we have one big error, and then for the blue line, we have a bunch of small errors. Which is smaller? If you take all of these red errors and you stack them on top of each other, is that smaller than 1? If so, that's a better line. So here, the blue line might be a better line. Even though it doesn't pass through the majority of points, the total distance could be less than this green line here. the bigger error. In particular, it's squared. So it's it's not just a distance, it's a squared distance. For reasons we will get into. Maybe not so much today, maybe next time. But that's from a pulled back perspective. If you understand this much, you understand the big picture about this entire approach. And you could define a different problem where you hit as many points as possible, and maybe that's your measure of the best thing to do. But in the case of linear regression, you don't care about moving the line or about having the line pass exactly through points. You don't care about that. What you do care about is the distance of the line on average from all of the points as a collection. And that's what this technique does. Okay? Yeah, we're coming up on the hour. I want to pause myself for 20 seconds because you guys don't speak out a ton, and just open this up to you for questions, thoughts. I get it. It makes sense now because of X, Y, and Z. In this example, I disagree because of X, Y, Z, or whatever. I'm lost. I don't care. What's the usefulness of this? Anything. I'll mute myself for 20 to 30 seconds to open up the floor to you guys. So let me do that now.
So one thing we're going over in my demand planning class is like mean absolute deviation. How similar or connected is it to this concept? 'Cause I feel like it's relatively.
This sounds like a really good question. I'm sorry. Could you repeat it? In some class, you're going through something an absolute deviation, and
Yeah, mean absolute deviation, where it's like the difference between the average and the point that it's at, and then you add all of those together and divide it by the average.
Okay, mean absolute deviation. Say that again. You add what together, and then you divide it by something.
Yeah. So one second. Okay.
I don't. I mean, I don't need like the exact mathematical formula. Just whatever it was that you said.
Yeah, you take like the sum of all the different collective points, like say if you're forecasting for January to December, so you have the difference in the average. You take the average of all of those numbers, and then you take the difference between those numbers and the average. You add all those, you sum all those, and then you divide it by the number of periods. So I was just wondering, like, 'cause it seems like loosely related in some way.
I think this sounds actually exactly the same.
Okay, yeah. I didn't. I
Differences.
wanted to say it was the same, but like I didn't. I wasn't necessarily sure.
Yeah. Is this fair? Again, like without the math, just so the this crazy looking thing on the left, that just means
Yeah,
the
no, that's
sum.
the sum. Yeah.
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 So I'm taking all of the differences and adding them together, and then I divide by the number of examples that I have to come out with the average difference. So
Yeah.
this is the average.
And that's why it's like it's because
Distance.
the sum is absolute. They put the absolute sign on it, so that's where the absolute comes from. Because it doesn't matter.
Very good.
I was saying earlier. With,
Very good. Yes. Right. So where this is the absolute value.
Yeah.
Yeah.
Exactly.
Excellent. Perfect. Yes, this is very, very, very related. Not exactly the same. There's
Okay.
some differences here. In particular, it's with the absolute value. So the absolute value accomplishes some of the things that taking a square does.
Mm-hmm.
Let me give a quick example. All right. Where you could take the absolute value or you take the square, and they're both good choices. Let's take this one. I don't know. I'll make this y equals x, and I'll call this point 1, 2, and this point 2 minus 1. Something like that. That's not quite right. 2 minus 1. Okay, something like this, right? So here 1, 2, and here's 1, and then here's minus 1. Let me redraw this. 2 minus 1, right? So there's the graph, and now let's look at the errors. That's an error. That's an error.
Yeah.
Actually, let me put this up a bit more. 1, 2. That's better. All right. So the what this does is, so this is a distance of 1. This is also a distance of 1 from the line, the point to the line, to the closest point that it could be on the line, right? So what this does is this gives an answer. Hold on. Actually, just make this a little bit more clear. 1, 2, 3, 4. Apologies, but this is going to illustrate the example a lot better. 1, 4. All right. Okay, pretty similar, except now this is a distance of 4, right? So this line, this point should be at 1, 1. It's at 1, 4. Actually, that's a distance of 3. And this point should be at 2, 2. 2 minus 1, sorry. It should be 2 minus 5. So this is a distance of 3, that's a distance of 3. The ideal point here would be 1, 1, and here the ideal point would be 2, 2. So here, this point is 3 above, and this point, wow, I'm so sorry. God, I'm really messing this up. 0, minus 1, minus 2. This should be here, minus 2, minus 2. All right. No, 2 minus 1. 0, 1, 2. Yes, great. All right. So for this y equals x line, this point should be at 1, 1. Instead, it's at 1, 4. So this point, if you moved it 3 units up, you would be correct. For this point at 2, 2, the actual point is at 2 minus 1, so you move it 3 units down, and you're at the right point. So using this is plus 3 plus the absolute value of minus 3 over 2, which equals 3. And so this is why you're taking the absolute value, because otherwise these would cancel each other out, right? You'd have a plus 3 and then you'd have a minus 3, which equals 0, and then you would have no error. because the line has some points exactly above it, the same way that it has points below it. But that doesn't make a good line, because now the line is still far away from points. So absolute value. You get this, which is wrong. Does that make sense so far? What I'm trying to convince you of is, why you take the absolute value. It solves a problem, which is you don't want points above the line canceling out points below the line with error. So if you take the absolute value, you don't care if it's above or below the line. You only care that it's not on the line.
Yeah, exactly. Yeah,
Okay.
it was just about measuring because it's like forecasting, so it's along the line. Like it doesn't matter if it's like above or below. You still want to not have that difference.
Very good. So this would be an error of 3. Agree?
Yeah.
All right. Now, what we're talking about is something that's slightly different. And it's different in an important way. Let's see what I want to do here. We'll do this one, whatever. What we're doing here is the sum of the difference squared over the number of examples. Okay.
Okay, so you're squaring it.
Right.
Yeah,
and that's
mostly
and
with MAD, or what I've seen so far is it basically just hovers around 1 or above. Like it'll be, if it's less than 1, it'll typically be like a lower type, but usually it's been like around like that would ultimately be 1.5.
I'm sorry, what's 1.5?
Oh wait, no, never mind. No, I'm incorrect. But yes, okay, I can see what you mean with the squaring. That's the important difference.
Right. So what this score is, let me just write it out real quick. Wow, where did that come from? What this is equal to is 3 squared, so 9 plus 9, which is 18 over 2. So this is 9.
Okay.
In one case we have 3, and in the other case we have 9. And the reason for the difference is because if you square the difference, you get punished more. Right? If these were a distance of 1 from the line, let me just make up stuff. If these were distances 1 from the line, then this would be equal to 1. And this would also be equal to 1. No difference. But when you get the points further away, they're not 1. Now the points get further away. That's at a distance 3. That's at a distance 3. You in this purple, you go from 1 up to 9. In this green red one, you go from 1 up to 3. So the further away points get, they're penalized even more here. So
to understand like the difference, like so like it's 9 there, right? But that's gonna be like relative to like what the usual variance is. You do like variance on variances.
So, I mean, actually, in purple here, this is the definition of variance.
Yeah.
That's the definition of it. This, in the green, that's not variance. This is something else that's kind of closer to a standard deviation. But in purple, this is actually the definition of variance. And so that's why I'm talking about random variables and expectation and variance, because in purple, that's what you're minimizing. You're minimizing the definition of variance. And there's deeper reasons behind this, but on more surface level kinds of things, one consequence of this is that when you square the differences, you punish points being far away by even more. They both get punishment, but when you square it, you're punishing it by a square factor. So it's like extra bad. You lose even more points when you square it.
What I meant, specifically on variance on variance, I understand that the purple is the definition of a variance. I meant more so that like you would take the difference of the variance and square it over the number of examples to see what like if there's volatility there. That's what I'm trying to see if that is
Right. Yeah. You're doing inception a little bit early. You're not taking the difference in variance. You're just taking the difference in distance. Just the regular old
yeah.
distance. But the distance you square, and then you sum them up and take the average. Or really, you take the average of the distances. So, man, what color can I choose? Here. This part, the sum and the division, that's the average. That's calculating an average. So both of these are doing an average. The first one is doing an average of differences. The second one is doing an average of squared distances or differences. Where here, the difference for both is how far away the line is from its expectation. These are both valid approaches to coming up with the best fit line. In fact, you can use either one. They will produce different answers. For reasons that are beyond the scope of this course, the second one is preferred in most cases. But this one up here, it solves many of the same problems.
Okay.
So you can use either approach, but this one down here has some other interpretations that are nice. Yeah, for this course, I'm not going to get into it. But that's a very good explanation or observation, and it's a very good observation that in one course you're learning this way, in this course you're learning a slightly different way. It's a variation. But that being said, there is a big overlap between the two. Yeah. I don't know which other course you're learning the other one in.
It's demand planning and fulfillment.
What is it?
Demand planning and fulfillment, like understanding like forecasting things, outside of like regression and like single and double smoothing, exponential smoothing, things like that.
Yeah. So regression is just fitting a line through points. That's what regression is. You have a bunch of points, you come up with a line, and then when you need to make a prediction, you predict it off the line. Whatever the line says, that's what your prediction is. How good that prediction is, that depends on the points that you have. Okay. So these are both of these are regression. Both of them are valid. In some cases, you might prefer one over the other. In the fields that I'm more familiar with, the purple one is better to use on average. It's not only, and as we talked about here, the absolute value, it's important that you're taking the absolute value. There's a reason why you're doing that. In particular, it's because you don't want to cancel out errors when points are above or below the line. These would cancel each other out because one would be +3 and the other would be -3. So those would cancel each other out. Or you can square it, and that also gets rid of negatives. But here in the purple, this has this deeper connection with ideas of statistics and probability, where it's actually being built from the definition of variance. And that's a rabbit hole you can dive into. And so that's why, yeah, somehow this is doing, by accident or by in interpretation, it's doing extra stuff. And so even though you're dealing with this variance, given different interpretations, you can be doing a lot of other things accidentally, or you can picture things differently, but the math is all kind of the same. And so when you're doing this one thing, you're actually doing another thing, and you can go back and forth between different areas of math, different whatever. Again, I don't want to get into it too much. Both
Okay.
are valid. It's a very, very good observation. That's a really good question. Thanks for asking it.
No problem. Thank you.
Yeah. Okay, we are pushing 3:15. Let's take a break. After this, if there's any questions, and that was an excellent one that we just had about what we just discussed, or about any of the things that I said here, please ask them, because this is as much today as I am going to be saying about this technique, which is where we're going in today's class. So we're crossing out this one, touching base on linear regression. When we come back, we'll be going back to like random variable kind of stuff. So for now, I'll leave this on the screen. Let's take a 15-minute break. We'll come back at 3:30. And if you think about this and you have some questions, please do ask, because having a big picture idea just makes life easier when you're doing math stuff. It's just whatever, like the math, just force it to agree with your big picture idea. And yeah, so after the break, I'll give a few minutes for people to ask questions about this should they have them. Otherwise, we'll just move on to continuous random variables. Thank you, everybody, and I'll see you at 3:30. All right, welcome back, everybody. Again, before we switch gears and start talking about continuous probability distributions, which are probability distributions with a smooth line. You can take any value you want. And then concentrations of measure. This is how far away you can expect to be away from the average. That's the rest of today's lecture. Before that, I'm covering high-level concepts for line fitting. As I said, I would open up the floor to anything about it. You're totally lost. What is this used for? Anything. I mean, I'm open to anything. So let me mute myself and I'll give you guys, 30 seconds or a minute to ask questions if you like. Okay, nothing. So, without further ado, let me start. First, let me quickly go over what we've talked about probability distributions, aka random variables. A random variable is a probability distribution. They're the same thing. Pick whichever one you want. I go back and forth between the two. But if I say one, I equivalently mean the other. And given any particular circumstance, if you prefer one phrasing over the other, great, choose that one. In any case, these are the same things. In general, I kind of prefer the terminology probability distribution better. First of all, just a quick recap. Probability distributions and random variables, again, the same thing. These are built on top of probability spaces. Probability spaces only care about events and the probability of those events. But the events themselves can be anything you want. They can be colors, they can be descriptions, they can be sentences, they can be videos, anything. Literally anything you want. Random variables take events and turn them into numbers. They keep the probabilities. The probability function, identical as the probability space that it's built on top of. But instead of talking about any event that you like, you talk about the number that corresponds to that event. Could be money that you earn, could be time that something takes. Doesn't matter. It's just some event that you interpret as a number. Great. So, the reason why I prefer a probability distribution is because I think that this picture is better. This is a nice way for myself. I tend to go to this type of picture, where I think of something of a mass of one being chopped up into pieces and being laid out, such that each piece is laying above a number, and the size of this cut up piece is reflected on the y-axis. But you take all of these pieces and you put them into a big ball. That ball is going to equal 1 pound or 1 kilogram, one whatever. Yeah, and in a lot of cases, this picture, I think, serves a little bit better. So we talked about different probability distributions. The one that we just saw, let me go back up to it. This is called a uniform probability distribution. All of the pieces are the same size. But there's no reason for that. You could have a probability distribution. Why? Like this. So all of these little pieces, these bars, if you collect them all together, they equal a mass of 1. But you don't have to place an equal-sized piece on every single number. You can place whatever sized piece you want above any number. When you collect them all together, they have to equal 1. All right, so in particular, this is the binomial distribution. This is one example of a binomial distribution. And the important part, or the qualities that this one and the one that we saw before have in common is that they are discrete. These pieces are over the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is there a piece over 2.5? No. No, there is not. You have to be the number 2, or you can be the number 3. That's the difference between a continuous and a discrete probability. I'll talk about that more in a minute. I just want to mention one more thing, that for probability distributions or random variables, let's take this one. It has 11 values, 0 through 10. So there's 11 altogether. That is it. In particular, this is how many heads you would, or no, how many balls a guy would hit out of 10 swings, given that he has a 60% individual chance of hitting a ball. Whatever. He can't hit 2.5 balls. He can't hit 7.2 balls. He has to hit 0 or 1 or 2 or 3 or 4 or whatever balls. So the value that a discrete random variable takes is among some fixed set of numbers. This is with hitting balls with a bat. Let me go back up here. This is the result of rolling a die. And a die can't be 2.8. It can't be 3.6. You roll a die, it's either going to be 1, 2, 3, 4, 5, or 6. There's fixed numbers. The expectation can be any number. In this case of the roll of a die, it's the number 3.5. 3.5 is not a number that shows up on a die. So in what sense is it the expected value? What this means is that over many, many, many throws of the die, if you average the numbers that you see, you can get numbers that are different than 1, 2, 3, 4, 5, or 6. If I get the number 3 one time and the number 4 the second time, then the average between the two is 3.5. So expectations, averages, can be any number you want. The result of a random variable, or if you sample a random variable, especially if it's a discrete random variable, your expectation can be any number. It does not have to be equal to one of the outcomes of an individual trial. Great. Now that we've covered that, hold on, before I delve in, any questions about that? I mean, I've talked about all these things before, but yeah, let me pause for a moment and see if I lost anybody. Okay, thank you for answering, Asher. Makes my life easier, really. It's super weird to just, boy, talking into the ether. Okay. Continuous random variable. So, quick picture. Discrete is a bar chart. Right, whatever. 1, 2, 3, 4, 5, 6. Doesn't matter. So long these things add up to 1, it's fine. Continuous Um, that's not right. All right, continuous, smooth. Anything that looks like this is a continuous random variable. Now, the area under each, this and this and this and this and this and this, all of them together have to equal 1. And here, same thing. All of the area under here, this added together has to equal 1. Okay, so it's still a probability space. Each of these are built on top of a probability space. Probability spaces are events that can happen where they have to sum to 1. All right, now we have an extra superpower of taking events and adding to look at them in terms of numbers. So I don't know, maybe this is 0 and this is 100. I don't care. Yeah, the area has to equal 1. Always. Okay, otherwise it's something else. I mean, you can do whatever you want, but if you want to talk about this area of probability, things equal 1. All right? Now, there are many discrete distributions. We talked about a couple of them. Let me go back very quickly. This is called a uniform distribution. Uniform, meaning everything is the same. Everything is the same height. Here, this is uniform. This is uniform. This one is binomial. Okay, those are the two that we talked about, basically. I mean, there's more. There's more. You're interested in it. There's fields of math that you can delve into. Okay. For the continuous random variable in this class, we're going to be talking about exactly 1. Only 1. And there's many. In fact, there's an infinite number of them. But in this class, we are just going to be talking about... Where's my pen? The normal distribution. Okay, I want to pause for a moment because I think most of you guys are second or third years, something like that. I think that this is something that you might have seen before or heard of before. So if you have any idea about it, I'd like to hear from you. And if nobody answers, I'm going to flip a coin and pick somebody. So... No brave souls. What's the question? The normal distribution, what is it? Or what do you know about it? Anything that you know about it. Anything that you've heard about it. Or that you might kind of think that you might maybe know about it. Whatever. All right. Oh, perfect. Emily. Yes. Oh, the bell curve. Very good. Emily, do you have a mic?
Hello.
Hey.
So yeah, I've just heard it as a bell curve because it's shaped like a bell with
Right.
like hump in the middle or whatever you want to call it.
Right. Let me draw something. It looks like that, kind of. Like a bell, as you say. Is what I drew, is that a bell curve?
The curve itself is
Yeah.
shaped like a bell curve, yeah.
Okay. How about this one? Is that a bell curve?
Yes.
Okay. How about this one?
Mm, I think so.
No, it's not. It's
Yeah.
this is actually the sum of two. So this is not
Oh.
a bell curve. Yeah. Okay. This is a bell curve though. The black one, bell. The purple one is a bell. Great. Yeah, the one on the right, it's man, it's a whole thing. You can believe it. Yeah, where you take two bell curves and you add them together. Basically, if you're dealing with one bell curve, life is easy. You go to two bell curves, adding them together, nobody has an answer. For hundreds of years, people thought about what do you do to come up with good answers here, and there's nothing that exists. You can approximate stuff, and you can have computers chug for a long time to try to make predictions, but simply put, life is bad. Like we won't talk about the whatever color that is, yellow or I don't know, yellow greenish. We're ignoring that, not in this class. But the other two, bell curves. What else about a bell curve besides what else can you say about them?
I guess you could say like the more samples or the more I guess yeah, the higher the sample size, the more likely it'll resemble a normal distribution.
How much do they resemble the normal distribution? That's a very good sequence of words. What does that mean? How much does I don't know, the black one or the purple one? I don't care, or a different one. How much? Let's take the black one. How much does that resemble a normal bell curve? What is normal?
I guess you could say normal is the uh, strongest likelihood of occurrence. Like over time, something becomes normal, meaning it occurs more frequently than others.
Hmm. Hmm. Yes, this is an unfortunate consequence of math plus language. We have more ideas in math than we have a vocabulary for in English. Sure, yeah. I mean, what you say is correct in English wise. Mathematically, a normal distribution is a very concrete thing. Let me ask you two other quick questions. The area under the black curve, how much area is there under this? Ooh. What's the area? Emily.
Not entirely sure. I can like talk through it, but I don't think it'll get to the.
Right, so I was just trying to emphasize this point 2 minutes ago. So, one way of representing random variables is, or probability distributions, same thing, is pictorially. Like you can draw a picture, which is what we're doing now. When you draw a picture, things need to be a probability space. For a probability space, what should all of the events, the probability of them happening, what should they add up to?
1.
Perfect. All right. Nailed it. There you go. Doesn't matter the shape.
Oh, okay.
Yeah, this would also be equal to 1. Whatever. Great. And so maybe it's easier the second time. What's the area under this? The purple one.
It would be 1, right?
It would be. Very good. Perfect. Thank you very much, Emily. Right. So these are, yes, this is called a continuous random variable or a continuous probability distribution. Stuff has to add up to 1, no matter the shape. There's really, really, really complicated shapes. In fact, you don't have to go so far to be in a shape category where everybody who's lived in the world so far throws up their hands and they can make a good, educated guess, but that's about it. Which is the one on the right, that yellow one that we're not talking about. In any case, you hit your 1 bell curve, solid. Everything's simple and nice. 2 bell curves, we're lost. No idea. It's bad news. Interesting that such minor changes can go from completely and utterly understood hundreds of years of writing to hundreds of years of nobody has any clue. All right. Anyway, that's not this class. But it is interesting, I think. So I talk about it. All right. Now, let me go back up. I'm not done with this yet. All right. Let me pick on another random person. Vincent. Do you have a mic?
Yeah.
Great. So I don't want to put you on the spot per se, but with random variables, with discrete random variables, they have 2 properties, no matter which random variable. So let me put this all, and I haven't emphasized this in class before, so I forgive you for not knowing the answer, but maybe you can ascertain an answer to this. So all random variables, all probability distributions have 2 different numbers that you can talk about to describe them. Do you have any idea of what one might be?
Did you say 2 different numbers?
These are 2 different numbers, correct? Yeah.
I'm not sure if this applies, but I know with like bell curves and like normal distributions and stuff, you can do like confidence intervals and that kind of thing.
Yes, you can. Those are based off of these 2 numbers. You might know the equation for a normal distribution. I'm going to introduce that in a little bit. But before I get there, there's, I don't know, one number is on top, one number is squared or divided or square root, blah, blah. In any case, you can define these things by 2 different numbers. Let me bring you back. Let me help you out a little bit. Here. Let me go up to... That works good. All right. So here's a probability distribution. And this is true for all probability distributions. We're moving into continuous, but this is the case for every single one. We've talked more about discrete random variables. is there any number that you see here that seems important for the probability distribution on the screen?
Yeah, I guess 1/6, because that's the probability for each of the random variables.
Yes, that how to say, good guess. Every number has to have a probability, but it's a different number.
Oh, is it 3.5?
There you go. What is that?
That's the mean.
Mean. Very
Yeah.
good. So you have the mean, aka the expectation. Now that you've guessed one, any guesses on the other?
Would it be the variance?
Very good. All right. Awesome. Right. Now, for I guess before I let you go, the mean, pictorially, let's take this black curve here. I'm highlighting again. What would be the expectation here for the black curve?
It would be like right in the middle at like, I guess it would like reach up at like the very top.
Very good. So that's the expectation. All right. And how about the variance?
Would that be a little bit on each side, like depending on whatever like the calculated variance is?
Okay, so if you look at the purple and the black ones, which one has a higher variance? And I'll tell you ahead of time, one of them has a high variance, one of them has a low variance. Which one would have the high variance?
The bell curve, or like the black one.
The black one. Okay, great. Yes, you're correct. Why the black one?
Because it's more spread out, and the purple one is more like concentrated to the mean.
Perfect. Thank you so much. That's it. Excellent. Yeah, so for every single random variable, for every single probability distribution, all of them will have these two values. They will have a mean and they will have a variance. Vincent made a very good observation that if it's fat, it has a high variance. If it's thin, it has a low variance. The variance is how much things are spread out away from the mean or away from the expectation. So on the right, it's fatter, so there's more values that are away from the middle of the bell. On the left, the purple one, the values are closer to the middle, so it has a lower variance. And no matter what, all random variables have these two properties. Okay? Now, I don't necessarily want to pollute this graph. That's the price you pay for making notes as you lecture. This in the red, I'll call this the normal distribution. What this means, it has a mean of 0, which means it should be centered. Let me do this. That means the center of the thing, right there, number 0. Like the peak of this thing is at the number 0. After that, the variance equals 1. All right, that's it. That's what a normal distribution is. Now, people talk about as Emily said, things being normal, and it means how close is it to the average and other stuff. Here, the normal distribution is a very concrete thing. Here, this normal distribution means this thing, the one in red. Exactly that. It is a bell curve that's centered right at 0. And how fat is it? It's as fat as that the variance is 1. Okay. Now, it turns out, and I don't know if we'll be able to get to this in this course, but if not, let me just talk broadly, quickly. You can change the black bell into the red bell. You'll notice that the black bell is to the right of the red bell. So you can shift the black bell to the left. And that way it's centered on the same spot. But the black bell is fatter than the red bell. But you can squeeze the black bell to make it thinner. Likewise, the purple bell, you can shift it to the right to be centered at the same point as the red bell. And you can also squash it down and make it fatter so that it's the same fatness as the red bell. That's the Cliff Notes on how no matter the bell curve, you can make anything a normal distribution. So no matter the bell curve, ignore the specifics. Just talk about the red one. Anything you can say about the red one, you can shift and squash or pull any other bell curve to be the red one. And then you can reverse the process. So anything you want to talk about bell curves, let's just talk about the red one and nothing else. Like anything that, we'll focus on the red one. Anything else, you shift it, you stretch it, you squeeze it. You can come up with another bell. But all of those things, the stretching and the squeezing, that isn't a big deal. It's a very simple process to do. But for all the interesting stuff about it, you can just talk about the red one. Yes, Olga says that this is perfectly symmetrical. That is true. Yes. So the amount of mass on the left and the amount of mass on the right are the same. It's perfectly symmetrical. Yes. There's other distributions that don't have that property. We're not talking about these in this class. I mean, we're talking about very kind of narrow stuff, but you could have something that looks like this, right? That's also a continuous distribution, but it's clearly not symmetrical. This is not a normal curve. This is not a symmetrical curve. If you look at the US cases of COVID-19, they kind of look like this, I guess, kind of. Well, I don't know. Actually, I don't know about, they look like this, up and then down and then flat. That's not normal either. So there's an infinite number of these things. In this class, we're talking about a very nice one, the normal distribution. Everything's nice and symmetrical. And the two properties about it, about the only one that we'll be talking about, because when we talk about this one, we're talking about all of them, all of the bell curves, not all distributions, but all bell curves. And that's enough. Anything you can say about this, you can apply to any other one that you want. All right, so I will leave it there. Oh, really quickly. Nice colors. So the normal distribution. It's written in this way. It's like a weird n, and then 0, 1. This is the mean, and that's the variance. And this is equal to 1 over the square root of 2 pi sigma squared. This is sigma squared. And the mean is mu of e to the minus x minus mu squared over 2 sigma squared. Oh boy, there we go. Just a bunch of math. I mean, we got square roots, we got fractions, we got pi, we got e, we got numbers squared, exponentials, just a ton of stuff here. That being said, after the break, which we'll be taking right now, we can come back at 4:25. I'm not going to explain everything about this, but I can demystify a bunch of this. This is just a bunch of math symbols thrown together, and who the hell can like decipher it? I despise giving equations and saying just use it. There's a reason behind this, and we will, through pictures, come to this thing, or at least most of it. I mean, it won't be so strange after the break. So let's take a 15-minute break. Let me see if I can get these things on the same screen. Kind of. So this thing in red here, this curve, is described exactly by this equation. The equation's super messy. It looks messy. We'll go over it. So, I don't know, reflect on the equation if you want, but more importantly, reflect on everything before. That all bell curves, we can only talk about the red one, and that's okay. We're safe to do that. It makes sense. Like, it's nobody's fooling anybody. That's the important part about things that follow, because I'm only going to be talking about the red one. So why is that okay? If it feels not okay to you, think about your question and raise it after our break. All right, see you guys at 4:25. Welcome back, everybody. Let's see. So before I delve into how to understand this equation, which I actually think is kind of fun, but anyway, this is the second to last week of class. As I'm sure you all know, these summer sessions are highly compressed classes that are normally taught over a number of months. We basically have a month for this, so I received pretty much universal feedback, in fact, exactly universal feedback regarding a midterm that everybody would prefer homework instead. So what I've decided to do is, as I said at the beginning of this class, to assign sort of a heavy homework. So however long the last homework was, it will be more substantial than that. The first homework you had a week. This next homework you'll have longer than that. But I want to try to collect the homework / midterm. They're going to be combined into one thing before our final class. That is, I hope, for your benefit, because come next Thursday, which will be the last lecture, I'm not going to be introducing new material. It will just be a review session. And so I'm going to try to grade as many submissions as I can before then, just in case you miss points on something and you're not sure why, or you're stuck on something and you're not sure how to navigate it, this kind of thing. So I'm trying as best as I can to try to save our last lecture just for addressing those kinds of issues and assigning the final that same day. I won't walk anybody through questions on the final, although the final, questions on the final, let me say this very quickly. It should be nothing that should surprise you, nothing that is tricky. I'm not trying to trick you. I'm not trying to, throw you questions that are on the face of them inappropriate or anything like that. So the kinds of questions that I ask on the homeworks are the kinds of questions you can expect on the final. Except for the homeworks, you have a week to work on them when I assign them. For the final, you'll have a day. So I'm not going to be, I think I talked about this the first day of class, but I'll repeat it. It will be a take-home final. You will have a bare minimum of 24 hours to work on it, probably something more like 36 hours. And you can use whatever resources are at your disposal. So it's an open book. You can look online. You can look at my videos. You can look at my notes. You can look at your own notes, whatever. Anything that you want, you can use it. The same thing for the homeworks. I will try to design the homework, or the final, I'll try to design the final such that you could reasonably finish it if you were well prepared within class time. Like as if I were to assign the final at the beginning of class and I'd collect them at the end of class. If you're paying attention, you feel good going into the thing and what have you, you should be able to finish the final in that amount of time. That being said, you don't just have class time to do it, you have more than that. The final is short answer, not multiple choice. There might be a mix. It's for sure the entire thing is not going to be multiple choice. We're in university. There might be some multiple choice, but again, nothing tricky. Insofar as there might be something tricky, it would be things that I've covered, I think, very well in this course. Your intuition is bad in this example. And so I'll ask maybe a similar question and I'll give maybe a multiple choice about things that people might drift to intuitively, like the Monty Hall problem, right? With the dragons and the princesses and stuff like this. It could be something like that, not that exact thing, but maybe like a small change, and it won't require pages of computation on your part. Hopefully it's something that, presuming that you understand the major concepts of what we covered in lecture, just in your head, you can feel out the right answer. But you'll be equipped in order to feel it out with the way of thinking behind it. So those kinds of questions might be multiple choice or, like just really obvious stuff. I mean, a probability space is made up of a sequence of events, true, false, or, we're a probability space. I've said it, I don't know how many times, I should keep a counter. It's two things. It's a set of events and a probability function that maps those events to some number between 0 and 1, such that all of those numbers add up to 1. Short answer, I don't know how. Maybe not. Maybe not exactly short answer, unless you consider the answers to the homework that you guys have done so far a short answer. If that's your definition of short answer, then yes, that will be included there. It will not have any heavier math or include any heavy mathematical symbols beyond what you've seen in the homework. And I know that I'm covering a lot more during lecture than I am during the homeworks, but to the extent that you could expect a question involving some type of mathematical computation on the final, it would be similar to the homework. Questions should be potentially slightly easier than the homeworks, because the homeworks you have a week to do. The final, I hope it's such that you could finish it within class time, but you'll have extra time to do it. I mean, I refuse to, this proctoring stuff, looking at webcams and tracking eye movements and stuff like that. Luckily, I'm in the position to teach the class the way that I want, and I'm not participating in anything even remotely touching that kind of technology. So that comes at the expense of basically longer until you get your grades back, I guess. But I mean, I'll do my best to have them back to you within a few days. That's it. And for the grades for the course, where we're at right now, we have one homework. We're going to have one more heavy homework that's going to be due next Wednesday, midnight, and then the final. I will update the course syllabus on Blackboard to reflect this, but I said at the beginning of today's class, let me say it again. What this means is that the final will take the same weighting as it did originally. All of the other weights, we've had no quizzes. I'll be combining the quizzes, the midterm, and the homeworks. Whatever weight those took up for the class is going to be absorbed by the first homework that you guys have already turned in, and the second homework that will be due next week. And then the final, which will be, 20-25%. So, any questions about that? I'll try to formally update the syllabus to reflect this, but I want to cover this before. Final is still 7.2 to 7.3. Correct. Right. So 7.2 next Thursday, I will assign the final probably before class. During class, I will be introducing no new material. The Thursday 7.2 July 2nd class will strictly be a review session. I will not answer specific questions about the final, assuming that I've already released it, except for clarifying questions. So you don't understand what I'm asking. Then I will clarify it, and I'll release a Blackboard announcement to all students of the question that I was asked and how I answered it. We provided an outline of specific topics just to narrow down our notes for the exam. Yes and no. I mean, during this class in our chat, I wrote down a list of topics. It will be something like that, a little longer, not much. But these are basically the highlights. During lectures, there's maybe 4 or 5 different sections, I guess, that I'd call it. There's probability spaces. This includes things like independence, discrete events, or disjoint events, excuse me. Random variables, that can be discrete or continuous. This will deal with maybe expectation, with maybe variance. It might be showing graphs and asking you to explain them, or it might be giving you a word thing and I ask you to draw a graph, that type of thing. And then linear regression that we've already started to touch on. Like we're hitting a lot of today. I spent some time talking about the high level concepts of it. This Thursday, about half of the lecture, I'll be using Excel to demonstrate linear regression with Excel. But nothing about Excel is going to be on the final. That's just for you guys to know a little bit more about Excel, and then also for this class, not just me drawing stuff out, but computing things and seeing, I don't know, programs output as you might normally more in the real world, depending on your position. Yeah, so sure, yeah, you will be receiving an outline of topics. I don't know exactly how specific they'll be, other than I won't ask anything that I don't include, but they'll all be very kind of general things. Yeah. Any other questions? Any complaints about that setup for the remainder of this course and the way that you'll be evaluated as far as grades? You can bring these things up now, or otherwise you can email me or message me privately if you have personal concerns. Yeah, but if you do, please let me know as soon as possible. I mean, next Thursday is our last class. Like we're in the last bits of our time together now. So if I don't hear from people soon, then it will be too late. You're gonna send us like a test file. So it will be just like the homeworks. I'm gonna upload a PDF to Blackboard. Yeah, and I would prefer, just like the homeworks, for you to upload it to Blackboard if possible. If for whatever reason you run into issues with that, you can email me. If there's issues beyond that, email me, email me. Get in touch with me, and I'll figure out what to do given the specific circumstances of whatever's happening. But that's about as much as I can do. Okay, so assuming that there's no other questions, again, if there are, please email me, get in touch with me, and message me privately, but do it as soon as possible, because the amount of time that I have for adjusting things in this course is rapidly diminishing. Again, we finish next week. So, all right, let's continue. Before I go into this equation and just where the hell it comes from, because it is a big mess. There's a lot that's happening in it. It's just a whole bunch of stuff. I want to rewind to our previous discussion about these three curves on the left. And in particular, why we can justify only caring about one of them. There's the purple one, there's the black one. I'm sure you guys have great imaginations. You can come up with all different kinds of bell curves of shapes and different locations. Given all of those different bell curves, I'm making the claim that we can just talk about one of them. Just one is enough. And in particular, because we can just talk about one, let's make this one easy to work with. We'll center it at 0, and we'll give it a variance of 1. I'll remind you that the variance is something squared, but 1 squared is still 1, so that's why it's chosen. 1 squared, 1, 0, and 1, those are nice numbers. And so let's go ahead and define a curve like that. That seems easy numbers. That's nice. Why is it that we are justified in only talking about a single curve among this entire family of bell curves? I talked about it before, but I want to hear at least one student give me their own impressions. So how about I pick on Mateo? Do you have a mic?
Yes.
Great.
Could you just repeat the question, please? I think you're muted, Professor.
My question is, why in all of the different possible bell curves are we justified in just talking and analyzing one of them? In particular, we care about this red one, the so-called normal distribution. There's lots of bell curves, but one of them is normal. That's this one in red. Why is it okay to just talk about this one when we're talking about any bell curve? We can just talk about this one, and somehow we can talk about all bell curves. How is that possible?
I guess because all other bell curves are just a variation of the normal distribution, and you could get to the normal distribution by, like we said before, either stretching it out or vice versa.
Very good. Yes, so stretching it out and shifting it. You can shift the thing left or right, and then you can stretch or squeeze it and make it have the same shape. Perfect. Thank you very much.
No problem.
All right. So, this is why in a lot of different circumstances, this is one reason why people care about the normal distribution. Because you can somehow talk about this one curve, and you're talking by extension about an entire family of curves, an infinite family. But you only need to actually analyze one of them. And okay. Now, let's go to where, and I'll keep these two things on the screen for the moment. This red curve. That's the pictorial version of it. On the bottom is the a different form of it. Same thing. They're the same. There's no difference. It's just different representations of it. Obviously, the pictorial thing seems simpler, I guess. Yeah, this equation has a bunch of stuff happening. So, again, I abhor giving equations and just having it be a black box. You should never memorize things. I mean, whatever, memorize things if you want, but I mean, understanding is much, much better. So, I am going to pick on maybe some random people. Let's see. Yeah, let me pick on random people. We'll build this together. So basically, the goal, I'll erase this, but the goal is to get something that looks like this. Oh, that's at the center, right? Let's construct this graph. And also not just that shape, but the area under this is equal to 1. because it should be a probability distribution. Okay, so how do we construct this? That's our goal. Like, that's where we're headed. So let's take some stuff that we know, and maybe a couple things that I can introduce to you, and build this. That's what we're going to do. This is what we want. That's where we're going. Let's construct it. So let me pick on, we'll build this up over maybe 3 or 4 pieces, something like that. How about, let me keep that here for now, I guess. Yeah, I haven't spoken to you today. Do you have a mic?
Yeah.
Great. Okay. We're going to be building up the graph up there by pieces. So let's that graph up there, here,
Mm-hmm.
it has a curve to it, like a nice smooth curve. So here's a graph that has a curve. I can make it better than that. For a graph of this type of curve, and let me meet the axis. What's the simplest equation that you know to make this type of graph, the one in black? Okay, let me ask you a different question. Y equals x. What does that look like?
Like a straight line.
Straight line. Like that, yeah?
Yeah.
Okay. How about y equals x squared?
Like the graph one.
Right, good. So that's it. That's the answer. Just for fun, what is y cubed?
Like a wave. The curve goes up and down.
Yeah, it kind of looks like an S. All right. Yeah, something like that. Cool. Excellent. All right. So we can forget y equals x. We can forget y cubed. Those don't matter. Let's stick with y equals x squared. That's the simplest way to get to this thing. All right. Now, let's draw a couple others. How about y equals x squared times 10? What does this graph look like? You can give specific numbers, or you can just describe how the shape changes. Just for a point of reference. 1, 1. 2, 4.
The shape will be the graph may look more thin and steep. The
More
curve,
thin and steep, so you think it would look something like that.
yeah.
Okay, let's check it. Let's take the point 1, 1. 1, 1 here. So that's, well, when x equals 1, y equals 1 here. When x equals 1 here, what does y equal?
Equal to 10.
10. Great. Okay, and when x equals 2 here, y equals 4. And so here, when x equals 2, what does y equal?
20.
Perfect. 120. Great. So, multiplying by a number makes this graph get sort of thinner, as you say. Okay? Now, last question. X squared over 2. What does this graph look like?
It will be more thick.
More thick. Okay. When x equals 1, what would y equal?
1/2.
1/2. All right, and when x equals 2, y is what?
Equals 2.
2. Perfect. So we have 1, 1/2, and 2, 2.
And maybe for the second graph, it should be 40, not 20.
Oh, yes, you're right. Wait, 40. Yes, you're right. Thank you. Okay, perfect. Okay, thank you very much. Yeah. So this is one component. All right. So the reason why we do this is because we want a curve. This graph up here, it's curved. So let's square stuff. All right. We're dealing with a curve. Now, I will give somebody a chance to speak out. This whole thing here, I'll call it x squared. 2. The next part, e to the x. If anybody is familiar with this, even just the way it looks as a graph, you can unmute yourself and come into the arena. Otherwise, I will pick out somebody.
Doesn't it look like a curve upwards, closer to the limits are closer to 0?
Curve upwards. So let me call this Q1, Q2, Q3, Q4. In which part of the graph should I start and where?
Well, it would start. How do I explain this?
Mhm.
At the axis in Q2, the vertical axis, you could
Right.
start there, keep the line close to 0, and then eventually curve up towards infinity.
Okay, like that?
The other way. It'll be closer to the origin at first, and then curve up outwards towards infinity.
You know, I think you can annotate my screen. Do you see this annotate button? Are you able to do that? Maybe you can just draw it for me.
I think I just requested it.
I'm looking around. How do I accept a request? I see nothing. Oh, very strange. Oh, okay. Allow to annotate. Got it. Yep. All right. You should be able to. I can draw a bigger graph if you like.
Yes, please.
All right. Great. I'll get rid of. Oh. What happened there? What? Oh, did I choose annotate? I did.
Oh no, I think I can also do that.
Oh, okay. I see. Let me get rid of this. E to the x. All right. Big axis there. Big enough?
Yeah.
All right. And
Oh, I
let me see.
just had to request it again.
Yep, you got it.
Okay, I think 10 in blue. Would be something. Oh, that was messy. How do I erase this?
Oh, don't worry about it. But yeah, I got the idea. Oh, good, you got it. All right.
It like starts close to this, and then it eventually goes like that.
Okay. Can you bring the graph more to the left? You're right. Yes, that looks very good. How does it look more on the left? Where does it go?
On the left, I'm gonna do it in green now. Like closer to this.
Oh, I see. Okay, very good. Perfect. Excellent. Let me turn off the sanitation and I'll redraw it. And I'd like to keep you here for a minute. So e to the x looks like this, right? Always above the x-axis. E to the 0, that's 1, right? Anything to the 0th power. So this is 0, 1. E to the 1, if this is 1, I don't know, it's 2.37 something. I don't know, whatever. And then it starts to kick in. Exponential growth is where, that's the thing that this embodies, exponential growth, which I was surprised in a class I was teaching for 3rd, 4th year students in the business school who didn't quite appreciate exponential growth. I won't get into it in this class, but I will say, if you're uncomfortable with it, learn about it. Google it, YouTube it, I don't care. But for anybody who's in business, have a good gut level understanding of what exponential growth is. It's super important. Like not just for you making money, which I hope you guys do, but also for you guys not like destroying society and like making horrible businesses. So exponential growth, please understand it. Something's gone bad if you graduate from an undergraduate position at a business school and you don't get exponential growth. Okay, that's as much as I'm going to say about it. Now, Emily, I would like to push you a little bit further, and I'll call this 2.5. And I'm going to ask you e to the negative x. So e to the x looks this way, exactly as you mentioned. What happens when you throw a negative into the exponent here? How does that change the curve?
Wouldn't it just be mirrored over the y-axis so that the increase is in Q1?
How about can you annotate? I'll allow you access, I guess.
Yeah.
That's great.
It would be something like that. Sorry, I'm doing this from my phone, so it's
no, it's great. Oh, sure, yeah, very good. Close enough. Thank you.
It should be above the x-axis.
Yes, it's always above the x-axis. In fact, it looks like this. So it never crosses the y-axis either. Yeah, this is e to the minus x. So basically this thing gets rotated this way, where this end comes but never meets the x-axis, and then this end meets the y-axis, sort of. That's what's going on with taking something to the negative power. Very good. So the closer you get to 0, I mean, e it just blows up. I mean, this number, e to the, I mean, e is whatever. Just replace it. 2.7, whatever. Call it 2. Is it 2.7 or 2. Man, I should know that. Is it 2.37 or 2.73? No, I'm thinking it's 2.73. Really?
I think it's 2.7.
That's what I thought. Thank you. I know. Man, Google. I typed in E on Google, the entire first page, E Entertainment. Disappointing. Yeah. Entertainment is way more important than math, apparently. Okay. Yeah, so 2.7 to, the minus 100. This is 1 over 2.7 to the 100. And so this becomes let's see. No, you can't have minus 100. 2.7, sorry, I got to make this less than 1. To the 1 over 100. This becomes 2.7 to the 100, which is a very, very large number. So after you cross 1 here, everything starts drastically shooting up. And then if you have 2.7 to like the 100, or to the minus 100, because this is e to the minus x, this becomes 1 over 2.7 to the 100, which is a really, really, really small number, which is why when you go out this way and you're at 100 here somewhere, I mean, this thing is like really, really, really small. Whatever. Great. So we're starting to cook. We have an x squared function. A couple things to notice about it. It's symmetrical about the x-axis. It's not exponential growth. It's polynomial growth because the x is in the denominator. E to the x, this is exponential growth. Things grow very, very quickly. E to the minus x is the same exponential growth, except it's more like exponential decay. This graph gets rotated about the axis. And so numbers start really, really, really big when they're under 1, and then they get super small as you go out. Okay. Why are we doing all of this? Why am I talking about it? I'm trying to get to this thing. Okay? Where is this coming from? So we already have e to the minus x. This part. We've already graphed it. Now, forgetting the mu, again, actually, we're working with the normal, right? With the normal distribution here. Sorry, this is the general equation. So the normal distribution here is going to be 1 over 2 pi, the square root. Sigma squared is 1, just placing it in. And then we have ex mu is 0, so we're not taking anything away. X squared. Over 2. Because sigma squared is 1. So this is the normal equation for the normal. This is in general. Let me put this here, actually. Oof. Mu sigma squared. 0, 1. All right. So this part on the left, we'll get to it. That's kind of boring. What we're just talking about is, what is this? What is this thing? By the way, this minus mu, that shifts left and right. This sigma squared makes things fat or thin. I'll leave that as an extra exercise for you, if you care. So we've talked about x squared here. And now we've talked about e to the minus x. Now we're going to combine them. What happens? 3. E to the minus x squared. We're combining these two things together. 2.178, thank you. 2.1, wait, 2718. All right, where am I getting 273? Maybe the golden ratio or something. Whatever. Thank you for the correction. I should know better. Okay. Great. Now we're here. Any brave souls want to tackle this? I'll walk through it with you if you happen to get stuck. Just as a reference. X squared. This is e to the minus x. Nobody. All right. Olga, we haven't spoken today.
Yes, I'm here.
Yeah, good evening. So this thing, e to the minus x squared. Let's talk about it. What does it look like?
Wait a second. Where is previous? There is picture previous.
Let me go up.
Go up.
This one?
Yeah, this one picture.
Yeah, I drew it here. That's this one.
Okay.
Yeah. So these are the two pictures. We have e to the minus x. Let me draw it a little bit better here.
This is. And the other side, it's we can draw this line on the other side. It's going to be. Oh no. Sorry.
Okay. There's a good way to approach this. Pick points. We'll just choose easy points that are easy to calculate, and we'll just put the point, and then later we'll connect them. How about when x equals 0? What does this equal?
It's a 0. It's a x0.
Mm-hmm.
A second.
So e to the minus 0 squared, which is e to the 0, which is what?
Wait a second.
Sure.
It's. I don't know.
Anything to the 0th power is the same number.
It's,
Does that help?
wait a second. Here we have 0 and 1. 0. Yes.
No, it's e to the 0th power.
Oh, e to 0
Yeah.
will be 0, right?
No, it's 1. I'll give that to you.
Yeah.
So here we have 0, 1. That's x equals 0, and y here, y is equal to that. All right?
Okay.
How about when x equals 1?
It's a 1. I don't know. 1. X.
This
second.
is You told me before. How big is e by itself?
E. Yes.
How big is it?
Oh no, how big is it? Wait a second.
You typed it in the chat. Look at your last message.
Oh, 2.718.
All right, great. 1 over 2.718.
I'm confused.
Okay.
Yeah. Wait a second.
Mm-hmm.
We have a one, it's an area, right? It's a one, it's a area.
Don't worry about the area yet. We'll get to the area. Forget that now.
Okay.
We'll get
Right.
there. Yeah, that's the very, very last thing. Right now, we're not concerned about that.
Okay.
Okay. So, where should I draw this point then? When x equals 1,
X
Um,
equals,
yeah,
it's
this
a,
y equals 1.
it's a two here.
I mean, is the here? I'll give you 3 choices: green, purple, yellow.
Okay. It's a purple. Go to purple.
Purple. What
Go-
number is purple?
It's 2.
2. All right. Is that 2?
Yes, it's 2.7.
It's 1 over that.
I mean, 1 over.
Yeah. This is 1 over. It's this number.
Yes, 1 over.
Right. So forget about this. Forget about the 718. About how much is that?
It's 2, right?
Yeah, about 1 over 2. So the which of the x's, the green, the purple, or the yellow, is best?
Will be wait a second. Will be will be yellow.
Very good. All right.
Yeah.
Very good. Yeah. So the yellow one. Let me get rid of these. Blah blah blah. Done done done. Get rid of that. All right. Sorry. Got to redraw some stuff here. Great. So here we have another point. There. We have a point here. We have a point here. Now I want to talk about -1. The point at -1.
Mm-hmm.
So if x is -1, and again y equals e to the minus x squared. What does y equal here?
1 minus 1. Here.
Plug in x here. What do I get when x is -1? I'll start
Here,
with-
I have to plug. I don't get it. This.
All right. Do you agree with that? Or are you lost somewhere?
Why you put 2 minus here? Here minus. Okay.
Right. So this minus here is that
Okay.
minus.
That's a yes.
Right. And then this minus is that minus. This -1 is that -1.
I got it.
Yeah. Okay.
Mm-hmm.
Okay. What is minus? So what does this equal? This thing.
Minus.
Yeah. What's -1 squared?
1.
1. Great. Okay. So this is equal to the e to the -1, and that's the same minus here.
Mm-hmm.
What is e to the -1? 1 over e.
One. So,
Sorry, really quick. Hold on.
yes.
2 to the -1. What does this equal? This. 1 over 2.
It's 0.1, 0.5.
Yeah, so this -1
It's
here in the exponent, it means you take this number, you put it in the bottom,
yes.
and then you raise it to whatever the power is. So 2 to the minus 2 is equal to 1 over 2 squared, or 1/4. Right? So the minus here just means
Why you put 2 over power of 2 over here on the bottom?
oh, this is separate. This is separate. This is just the rules of taking minus exponents. This is how to write minus exponents here. What does that mean if you take a minus exponent of something? Okay, 2 to the 1 is 2. Agree?
Yes.
All right. How about 2 to the 2? 2 squared.
It's a 4.
4. Perfect.
Why you why
Right. So
why did
here,
okay.
yeah. So what I'm saying is that in the same way that these are exponents of positive numbers, if you take an exponent of a negative number, things are the same on the bottom. You have 2 on the bottom, you have 4 on the bottom, but
Yeah,
they're on the bottom because of this minus number in the exponent.
minus is a cancel. Or we have a positive number. We have a 2 over 2 over here. Yeah, I got it.
You got it? 2 to the minus 2 is 1/4.
Yes.
Okay. Sanity check. 2 to the minus 3 is what?
It's it's a 8.
There's an 8 in there, yes.
But yeah. So
Is this equal to 8? Then what's the difference between this? 2 cubed and 2 to the minus 3.
because of minus and negative. I don't
Are
know.
both of these 8?
No, it's not. It's
Yeah.
not. It's negative. It's not.
Yeah, so the top one is 1 over 8.
This is gonna be yes. It's
Yeah. So that's the difference. I mean, so this minus puts whatever the number is in the bottom. Right? It's 1 over whatever the number is. So 2 to the minus 3 is 1 over 8. 2 to the 3 is 8. 2 to the
Yes.
minus 3 is 1 over 8. So the numbers get smaller. The more negative, the smaller the numbers get. From 1/2 to 1/4 to 1/8. These numbers are going down, right?
yeah.
Okay.
I think this is simple, but some with that simple things sometimes like a confusion. With,
Understood. Yeah, I know. Yeah, I have to do sanity checks myself all the time. Yeah, start with really simple things and go from there.
I still don't why you take 2 a negative 3.
All of this is to explain. Here, let me segregate this. What are negative exponents?
Oh, okay, gotcha.
Right? That's where I was focusing on it. I figured 2 is easier than E to work with. That's why. Yeah. All right. So because here on the left, what we care about is that now we have here e to the minus 1. And e to the minus 1 is 1 over e. Do you see why that is?
Yeah.
It's the same thing here.
Okay, 2. So E is okay. It's a number E. 2.
Right. Same
Okay.
logic. Same logic.
So E we assign as a 2 goes a number, right?
Yes.
Yes. Okay.
Yeah, sure. Yeah, replace E with the number. E is just a letter. You don't have to think about the letter. Replace it with the number. You can do anything you like, so long it makes sense to you. So, okay, what we've done so far is we've graphed 2 points on this thing. The first, when x is equal to 0, that's an easy thing to do. And we found the number 1. Because anything to the 0th power is 1.
Yes.
We got the second point here at approximately 1 1/2. This is, this is the point 1 and 1 over 2.718. For this reason, x equals 1. And because we're thinking about e to the minus x squared, we just replace x with the number 1. 1 squared is equal to 1. E to the minus 1 is 1 over e. And then we just replace e. So that's about 1/2. Something like that. Right? We don't care about the exact thing. Just roughly. Okay? So that's how we got these 2 points.
So what's graph is gonna be?
Let's find out. We need another point. Maybe another 2 points or 3 points. But right now we have 2, and we're working on the third point. So we're looking at this line here. When x is equal to minus 1, where should we put the point on this vertical line? So we take x equals to minus 1, and now we're trying to figure out the y, the vertical axis. How far up or down should we put this point?
We have to put the point up, right?
Okay, right?
It's
How far up?
It's gonna be 2.
2.
Yeah.
Hold on. Let's see.
No.
Yeah, it's not 2. Do you know how we got here? The 1 over e?
Yes, it's a minus. It's a e minus 1 square goes to.
I'll give you a hint.
I mean,
Give you
here.
a big hint.
From that.
Okay. So where is the point? Let me give you 3 choices again. 1,
Yeah.
2, 3. Which X? The blue, the green, or the yellow?
I think it's a blue. No? Wow.
It's not the blue. Why do you think it's the blue? All right, so what over E?
You said the line is not going to be on about line, it's above there, right? So,
I'm not trying to say anything. I'm trying to have you come to the conclusion yourself.
no, I'm not going to get to the conclusion. Okay, so, yellow. Let's yellow that on the bow. That's X.
You're a horrible guesser. It's
No.
really bad. No, yeah. All right. Thank you, Olga. Hold on. So, yeah, because we have 10 more minutes left. Thank you so much for sticking together with this. Yeah, thank you. Let me pick on somebody else I haven't picked on yet. Sean, I haven't heard from you all class, I don't think. Do you have a mic?
Yeah, what's up, Professor?
Great. let me clean this up a little bit. So my question is, right now I'm just trying to draw this graph, e to the minus x squared. And a good way to draw a graph, or a good way to start, is to just plug and chug. Put in easy numbers and calculate where the points are, and then you connect the dots, basically. Here we've drawn 2 points. Do you understand where these 2 points came from?
Yes.
Great. All right. So for the third point, I'm focused now on this -1. So it's going to be somewhere along this line. I just want to know how far up on that line this is. So where is the point? Like how far up on?
I would think that it would be at 1 because negative 1 would be 1. So 1 square will be, or no, 2.7.
2.7. But it's e. Okay, hold on. Let's go rid of the e. Maybe that's confusing. Let's get rid of all that. I'll replace it with 2.7. Okay. 2.7 to the -1 is 1 over 2.7. Did I lose you?
No, I'm here.
Okay. No, I don't mean electronically. I mean logically.
Oh no, yeah, I'm understanding where you're coming from.
Great. So, what is 1 over 2.7?
Like 1 over e.
Correct. To throw out a number, a rough number. You don't need to be too accurate. Is it 10? Is it 2? Is it a half? Is it minus 100?
It's less than half. but
Less than a
it's-
half.
Yeah.
Great. Less than a half. So, okay, I'll ask you the same question. 1, 2, 3. Is it the green X, the purple X, or the red X?
I would argue the purple.
The purple. Very good. Okay. Did you ever play Connect the Dots when you were little?
Yeah.
Okay, great. I'll ask one more question. Well, 2 more questions, actually. Let's blow this up. So we're talking about e to the minus x squared. Let's do x equals 100. What is y?
Y would be e to the 1 over 100. Or 1 over 10,000. So it'd be
Oh,
e to
yes,
the
yes,
negative
yes, yes.
100
yes.
squared.
Right. So this is 1 over e to this big number. Is this a big number or a small number?
Very small number.
Very small number. Okay, so when x is way down here, we have a really small number. How about, does this change if I make x equal to minus 100?
No.
Same number, right?
Yeah.
Okay, so symmetry. We have symmetry, so this is way down here. Now, let's connect the dots. What does this look like?
It's normally a flat, almost a flat line until it reaches these 3 where the little curve would come, and then it would go back to approaching the x-axis.
Is that a fair curve?
Yeah.
Great. Thank you. Very good. Thank you so much, Ishan. So this is what the graph of e to the minus x squared looks like. It looks like this. E makes things go really small when you go far away. But E e to the minus x, I mean, it's sort of only in one part of this graph. So how do we get e to cover the entire x-axis? Well, we can square stuff, because then negatives are okay. So we get this type of looking of graph. All right, that's our basic shape. That's it. That's where the shape comes from, which is what I'm trying to convey here. Let me go back up here. This red curve, where does it come from? Or the red curve is easy. Fine, it's a red curve. Where does this equation come from? You've got e's, you've got e's raised to some power. Focus on the normal curve, which is e to the minus x squared. Forget the over 2. That makes it fatter. The last part is where does this 1 over 2 pi come in? This comes in because the area under this curve doesn't equal 1. It's too much. In fact, the area under this curve, let me do this. The area equals 2 pi. You can calculate it. It's beyond the scope of this course on how to do it, but you use calculus. The area under this thing is 2 pi. I promise you. But we want a probability distribution. And the area in probability distributions is equal to 1. I'm sorry, this is the square root of 2 pi. The probability distributions, I mean, the area has to equal 1. So how do we get the square root of 2 pi to equal 1? Divide by the square root of 2 pi. Bam! This number here, if you calculate the area under this curve, it's going to be the square root of 2 pi. So let's make the thing equal to 1 by dividing by that number. That's where all of this comes from. Hopefully, this gives some kind of intuition about where this equation is coming from. We want to construct this. This is our goal. We want to construct this shape where the area equals 1. So we use a couple of equations, basically x squared and e to the x, and play with stuff to come here, e to the minus x squared. And the reason why you do that is because it gives you this nice curve. It gives you the general shape. The only property it's missing is the area. And that's why you divide by it. This isn't a calculus class. I'm not going to derive why the area under the curve is this, but you can just trust me on it. So yes, and thank you, Royston, for commenting earlier. You're correct. This point is the same one. It's symmetrical. It's symmetrical. Which, as somebody said earlier about bell curves, they're symmetrical. They're the exact same on the left and the right. The exact same. Why is it the exact same on the left and the right? Because it's built on top of this x squared, which is the same on the left and the right. That's the property that this x squared has. So let's use it to make things look symmetrical, because why? I don't know, we want it. All right, so that is it. Thank you guys for listening to that. I hope that now when you look at this really weird equation that has square roots and pies and e's and minus exponentials, it feels a little bit less scary, because you kind of know where it comes from. There are some calculus details to figure out numbers and blah, blah. But, I mean, we did it here. I mean, this is the main idea. You construct it. So that's where all of this stuff comes from. This looks scary. There's a lot happening, but it's not so scary from certain perspectives. And the only thing that this minus mu, is doing is shifting left and right. And the thing that this sigma squared here and here is doing, it changes the fatness. So a mu will shift left or right. And if you want a fatter thing, you have a bigger variance. If you want a thinner thing, you have a small variance. And that's it. So, okay. Review the last part at the beginning of next class. Got a little lost. I will do that next class. I will do that. Yeah, this is, it's, well, maybe a lot to get through. This is definitely the most theoretical math part of this course. I'm not going to ask you anything related to deriving these things or anything like that. It's more just that I have a deep belief that nobody should just be given an equation and told use it without having some basic idea of what it represents. And I'll spend time on trying to do that. We'll cover it again at the beginning of next class. Great. Thank you, everybody, and I will see you on Thursday.